So the first thing I want to do is look at a couple problems from the homework that's open right now, the one that was going to be due last night, but it's now due at 5. Let's look at number 4, going by what you guys missed the most here. Number 3 and number 14. The review that I put together doesn't have the most recent stuff on it because it's the most recent. So we'll do a couple of these that you guys had more difficulty with, and then we'll review everything up to chapter 6. And then you got your practice review set, homework set, and then we'll take the exam on Wednesday, okay? What did I say? 3 and 14? Is that what I said? Number 3. No, that's the wrong one. Let's see here. Up here. Okay, number 3. Okay? Oh, this is the whole thing, huh? So it says sketch normal distribution with mean of 1 and standard deviation 5. So then, where's the center of the data going to be? It's going to be centered around 1, right? The mean is the center of our data, so that eliminates B. Standard deviation of 5. Remember what I told you about the trick with this? I'm going to So if you have a standard normal curve like this, okay, so of course we know that the mean is here. And how much of the data lies within 1 standard deviation of the mean? Do you remember? 68%. Okay, so that's something like this. So within that range right there, that's 1 standard deviation. It's not the best drawing. But that area right there and that percent of the data is 68%. So this is mu plus 1 standard deviation, and that's mu minus. And so the little trick I gave you was there's kind of a flat part to the curve here, and then it flattens out again. And so then in the curve part, you look for kind of where it's curved the most. So maybe right here is kind of like where it's the most curved because it's flat over here and it's flat over here. Right around there, just as a rule, just kind of as a general sketching, that's your 2 standard deviations above the mean. Same thing over here. So flat, flat, so somewhere right around here is your 2 standard deviations above the mean. Or below. No, it's below. So now we've got these 2 to choose from. From 1 here, they've gone up 5 and down 5. This is 1 plus 5 and 1 minus 5. And then here they've gone up 10. 1 plus 10, that's 11. And 1 minus 10 is negative 9. So based on the little trick I showed you, which one is going to be, for a standard deviation of 5, which one is going to be correct, A or C? Yeah, because so if you're looking at this curve, then it's going to be somewhere right to the flat part, and then it's flat. So right around there is going to be that 2 standard deviations above, and kind of right there where it's kind of curved the most, 2 standard deviations below. Well, this is only 1, right? That's only 1. 1 standard deviation is going to be more like this. That's your 1 standard deviation. So this can't be right. It has to be this one. Now, you guys get multiple attempts on the problems, right? And in fact, I think you get 3 tries on a particular problem, and if you still haven't gotten it right, then you get another chance at it, right? It's just 3 tries on the first one they give you?
Yeah, occasionally there's a problem where they
Oh,
do 3 tries.
okay.
And we're on one of the other ones I had that problem.
Well, that wasn't, so I guess this on multiple choice, that's like an automatic thing, because I set it always for 3. I set it always for 3. So I guess that this one, there's an override in the system. So you got to get it right on the first attempt, which kind of makes sense, because there's only 3 choices. But does that make sense now? Okay. So what was the other one? 14? Oh, and so let's talk about this 2. So we know this one's right over here. We said 1 standard deviation above and below is what percent of the data?
60.
About 68. And then what about 2 standard deviations? 95. So 68. That's 1 standard deviation on either side of the mean. That contains 68% of the data about for a large population. If you have a small sample, these numbers could vary quite a bit. But if it's a normal distribution and you have a large population, then you get really close to these numbers. 68% of the data, 95% is plus or minus 2, and then what about plus or minus 3? 99.7% of the data is within 3 standard deviations. So virtually all of the data is within 3 standard deviations of the mean. Okay, let's look at 14. Hopefully this is a little more substantive. Okay, so this is this z of 0.6, z alpha. So z alpha, and alpha is the area to the left or to the right? This is to the right. So this is it's a little bit counterintuitive because we know that everything in our table gives us an area to the left. Every single number in the table that we have is a number to the left of the z-score that we put in. But the z alpha notation, this little subscript here is giving you an amount of area to the right. So we've got this one is z of minus z of 0.6. So therefore, in the table, what are we going to look for? We're not going to look up 0.6. We're going to look up what? 1 minus, hello. Is that 0.94? So is that a z-score or is that an area? 0.94. Is that a z-score or is that an area? That's the area. That's where you're going to go in the middle of the table, and you're going to look for 0.9400. We're trying to figure out what z-score gives an area of 0.9400. Anybody got it? Look in your table. So just pick the closest one. Find it. Go away. Okay. .9400 is going to be, so there's 0.93, is it right in between those two? Yeah, so it's halfway between. So what are we looking at? 1.55 or 1.56? So we got to see what they want the answer to be. So 1.55 or 1.56. Agree with that? Round to 2. So rounding up would be it'd be 9.555. So that would round up to 1.56. That's what I think I want. Okay, so let's see here. 2 decimal places as needed. So my only possibility is 1.55. Okay, good. So remember the Z alpha notation, it's you're finding the Z-score whose area is your alpha, and that alpha area is to the right of the Z-score that you want. Okay, so there was general high level of success in all the rest of the problems. So this chapter 6 homework, it's not part of like I said, it's not part of the review set that I put up for Wednesday, but it's definitely on the exam. Oh no, I'm sorry. It is part of the review set. There's problems in the review set. It's just not what I have for you in class today. So let's go back to the beginning. Okay, the first thing that I want to talk about is this is a random number generator, and it's used to find like a list, make a random list. So, let's say there's 34 of us in here, and we're going to have a lottery. And say we want to let's use row 15. So you pick 5 winners. Okay, so if we numbered all of you from 1 to 34, and we're going to use row 15 to decide who the winners of our lottery are. See if you can remember how to do that. Who are the 5 lucky winners in our lottery if we number all the students in the classroom from 1 to 34? So I said this row right here. So who's the first winner? Lucky 7, right? So you remember that you have to, if it's going to be 1 to 34, you have to always pick pairs, right? Even though 1 through 9 is a single digit number, you still have to, it would have to be 0, 1 or 0, 2 or 0, 8 to get one of the first 9. So the number that you're picking per group has to stay the same. You're not going to pick 7 and then pick 23 and then pick 8. It has to be 0, 8. Okay? So number 7. And then 85, we cross out because it's not between 34. And then 14. And then 74 we cross out. And then 52 we cross out. 66 is gone. 74. 28, is that 3 so far? 33 and 31. So who was it? 7, 14, 28, 33, and 31. Come claim your prize after class. Okay? Do you remember? Does that make sense? Any questions on that? So just a way of picking 5 random numbers. A little bit dated, right? Because we got lots of technology and computers that could do this kind of thing. Okay, and then so the next thing was given a data set, it was organization of data. So into tables and histograms. Remember we did that in the first week. So let's have you guys do this. This was with limit grouping, right? So there were single class values was one particular way to do it, but then another way was to make groupings. So we would tally up. This is days of maturity on a certain loan, so we tally up, and then the frequency. Remember what the frequency is and relative frequency. Frequency is just a plain old count, just how many. And then the relative frequency was like the fraction of 1, right? The fraction of 1. Okay, so much work on this. Give this a try. Okay, 30 to 39, I see 1. Is that right? Hiding. Wow. Just 2? 40 to 49, I had 1. Eight, I had for 50 to 59. Seven, I had for 60 to 69. I had 4, is that right, for 70 to 79? One and 2. I guess I should have just put this in over here. This should be here. Okay, so 2, 1, 8, 7, 4, 1, 2. Okay, and so then the frequency, if you total up all the frequencies, it's the total number in the sample or the population, whatever you're doing. So the total of frequencies should be your total in the sample. Okay, and then the relative frequency is then the same, it's the same information, but as a fraction of 1, right? As a fraction of 1. So 2/25. Is that like 0.083? And then this is 0.04. .32. And then what's this? 0.28. Okay, and the relative frequency should add up to 1. So if it's like this is kind of like what fraction of the data is that particular limit grouping. So if you add up all the different groups, you ought to get 1. And so then we can ask questions like, what percentage of the investments mature in 50 to 69 days? So you look at those two, right? So you look at, 0.32 or 50 to 59, 0.28 are from 60 to 69. So this would be 60%. Okay. What percent are not greater than 80? Not greater than 80 days. So what applies here? Kind of two ways to do it. There's a longer way, and then there's kind of a more clever way. That's easier. Yeah, Scott. 80%. And how'd you get 80%? That shouldn't be 0.8. You're close. 80%. What's that? 80%. Yeah. So you could add up all the ones that are not greater than 80. Add up all those, or you could add up the ones that don't qualify and subtract from 1, right? So you had a 0.04, 0.8, that's 0.12. Take 1 minus that. That's the most efficient route here. 1 minus 0.12. Just everything that we don't want. These are all the ones that are greater than 80. So 88% of the investments have a maturity date greater than 80 days. So what's the probability? So what's the probability that if you picked an investment at random, its days to maturity is not greater than 80? Yeah, so remember when we got into probability, we said, oh, probabilities are really like the twin brother of relative frequency. They're like the exact same thing. The portion of 1 is the same as if you picked 1 at random, the probability that you would get that, right? The likelihood. Okay, so remember relative frequency and probability are like, they're almost the same. They're very, very similar. They're the same value, right? They're same value, they're just a slightly different way of looking at it. So it's like this percent of the investments, 28% of the investments are between 60 and 69, which is the same thing as saying if you pulled 1 at random of all these, there's a 28% chance it would be one of those. Okay, questions on this? Okay, so stem and leaf diagrams. So this is cholesterol levels for 20 high-level patients. So this is an example of 1 line per stem, meaning so here's stem. We just have 1 stem for all the ones that start with 19, and then we just have 1 stem for all the ones that start with 20. Okay, so let's just interpret here. What do these 2 8s mean right here? So what's the meaning of those 2 8s right there? When you look at this diagram, you see those 2 8s. What does it mean? What's that? Okay, so talk to me about cholesterol patients. He said there's 2 patients with a cholesterol level of 208. What do you think? It's exactly what that says, right? So we got, you put the numbers together, 208, but then there's another one, 208. So where are they? There's one, and there's the other. So that, you read that there's two patients from this sample, or from this population, that have a cholesterol level of 208. Okay, so now 2 lines per stem would mean we break up the 19s into 19 and 0 through 5, and then 0 through 4, and then 5 through 9. So you had 0 through 4, and then all the ones that end 5 through 9, and then all the ones that start 0 through 4, and then end 5 through 9, etc. Okay, so why don't you make that? So make the 2 lines per stem version of this, which is very easy if you have the one stem per line, or 1 line per stem. Okay, so what's going to go in the first line here? Nothing. Second line? 9. Okay, so then this first line, first stem, 20. It's going to be everything up 0 through 4. So 0, 2, 3. And then this will be 5 through 9, the ones that end in 5 through 9.
7, 8, 9.
Yep. 21. So we're going to have everything 0 through 4. And then? And then 22. And we should probably put the other 22 here, and then we would just leave it blank. Questions on that? Okay, and so then we had different ways of visually seeing a distribution. So we had the histograms with the bars. The height of each bar is the frequency in that category, right? This also is showing that same thing. It's just showing it left to right. So, or showing kind of the bars sticking to the right. So that's what we had. So if we take those stem diagrams and we turn them on their side, then it looks like a histogram, right? So in this values of the variable between 21 or 210 and 204, we have this many. So it's the highest frequency. So, and then we talked about shape of the distribution. Is this one skewed right or skewed left? You're all saying left. Because what is to the left of the other? Is the mean to the left of the median, or the other way? Is the median to the left of the mean? That's what the skew is about. It's about where one of those is in relation to the other. So is the mean pulled to the left, or is the median pulled to the left? Okay, where's the median? Where's the median of this? You could guess that the median is going to be right in here, right? But what about the mean? Because of this, because there's more data further away from the median on this side, that's going to pull the mean this way. Okay, so that's why it's skewed left. Because the middle of the data is going to be around in the low 21s. But because we have this data down here around 19 and 20, that's going to pull the mean to the left. And so left means, this is key, lower values. So the mean is pulled down in value. And so we say that's left because that's conventionally how we increasing numbers go to the right. Okay, so skewed right means the mean is pulled toward higher values. Okay? So if for some crazy reason I had my lower numbers here, all right, and increasing this way, then this would be skewed left, because left means lower values. It's only, we call it left just by our convention, okay? So skewing left means the mean is pulled towards lower values than the median. And pulling right means the mean is skewed towards higher values than the median. Questions on that? Okay, so here's a histogram showing, what is this? Household size, number of people in the household. And this is relative frequency histograms, so these are percentage or portions of one. Skewed left or right? He said right. This is right, right? Because our median would be in here around 2 or 3. But because there are some households that have significantly more, 6, 7, maybe 8. Our median's in here. The data up here is going to pull it to the right. So pull it towards higher values, right? It pulls the mean towards higher values. That's skewed right. Okay, so remember mean, median, and mode. The mean, it's your arithmetic average. You're going to sum up the observations, divide by the number of observations. You guys all know that before you started this course. Median is the middle value. What if there's an even number in the list? How do we get the median? There's 2 middle numbers. You take the mean of the 2 middle numbers. You take the mean of the 2 middle numbers if you have an even number in the list. If there's an odd number in the list, you're home free. There is one exact middle data value, right? Okay, the mode is the most frequent. Okay, there can be no mode. That means that every data point or every observation is a distinct value. So there's no repeats. That would be no mode. And then you could have multiple modes, which means that the most frequent value, there's like a tie for the most frequent. So you'd have 2 modes, 3 modes, 4 modes, if there's a tie for the most frequent. Questions on those? Mean, median, and mode. And all of these are measures of the middle of the data set. Mode measures the middle when you have a large population. Like, so for this sample, what are these? I think these are like costs of DVD players or something, or televisions, I don't know. But this is not, see the mode here is 300. That's not an indication of the center, right? A better indication of the center would be like the median or the mean. The most frequent is like the lowest value. But if you have a normal distribution and a large population, then that mode becomes, right? The mode becomes a measure of center as well. Because what does our distribution look like? It looks like this. Where's the most frequent? Where's the most frequent data? Well, the highest part of the curve, which is in the middle. So your mean, median, and mode for a normal distribution all indicate the center of the data set. Okay, we talked about this. Again, here's a good picture. Right skewed means, again, the mean is higher value than the median, higher numerical value. And left skewed means the mean is a lower numerical value than the median. Symmetric means they're about the same, like our normal distribution. Okay, quartiles are based on the median, right? So the second quartile is the median. Remember that? Then the first quartile is the median of the bottom half of the data set. And the third quartile is the median of the upper half. So what do we get? We get 25% of the data ranges, right? So we get the lowest 25% is the first quartile. And then from the first quartile, the second quartile is another 25% of the data. Similarly, second to third, third to the max. Okay, so the quartiles break up the data set into 25% frequencies. And they're all medians. That's the median of the whole set. That's the first quartile's median of the lower half. Third quartile's the median of the upper half. Okay, the interquartile range is the difference between the first and third quartiles. So you get the median of the upper half minus the median of the lower half. What percent of the data falls in the interquartile range? What percent of the data falls in this range? Be 50%, right? Be the middle 50% of the data falls in the interquartile range. Okay, and then the 5-number summary is simply the min, Q1, Q2, Q3, and max. Okay, so that's the 5-number summary. And then be careful that we're going to look at the box plot. The box plot has a different set of 5 numbers, okay, than the 5-number summary. So the 5-number summary is very simple. It's just the min data value, the 3 quartiles, and the max data value. All right, now these box plot is a little bit different. You use the 3 quartiles to make the actual box, which is that's your interquartile range right there. From there to there is your interquartile range. But then you don't use the max or the min necessarily for the ends of the whiskers, right? It says box and whiskers. So the ends of the whiskers could be one of 2 things. Down here, this could be the min, or it could be what's called the lower limit. So this is the min, or the lower limit. How do you know which one it is? Well, whatever's greater, okay? So you find this lower limit. If all the data is greater than that, then that's what you put for the end of your whisker. But if you find that lower limit and there's another data value or two outside here, those are potential outliers, and you use the lower limit to be the end of the whisker. So in this case, is this the min or the lower limit? Is that the actual lowest data value there at the end of the whisker, or is it this thing where we took Q1 minus 1.5 of IQR? This is the actual min. Okay, why? Because there's no potential outliers out here. So this is the actual min of the data set. Same thing here. This could be the max, or it could be the upper limit. Whatever is less. Okay, whatever is less. So which one is this? That's the upper limit, because we've got this outlier. They're showing us this outlier in the data set here. So that could be, it's either the max or the upper limit. And in this particular box and whiskers diagram, it's the upper limit. Because the upper limit is going to identify that the max and maybe one other is not is a potential outlier. And so what's the solution for finding the center of the data if you have outliers? Remember that? If you have outliers, which measure of center is the one that's accurate? Yeah. Yeah, the median, right? Because the mean is going to add that value in, and it's going to skew it, in this case, to the right. But by using the median, it negates the effect of that. And that's why this Q2 is an accurate display of the middle of the data, okay? Because that outlier is just one, its value isn't pulling up the median, because the median is where half of the data lies above and below, regardless of how high or low that is. Okay, so the median is our remedy to get the center of the data set when there's potential outliers. Questions on the box and whisker plots? Okay, and then you remember the standardized variable, finding Z-scores. So it's a way of comparing different distributions with different means and different standard deviations. Turn it into a Z-score. And what's the meaning of the Z-score? What is that measuring? Do you remember? What does a Z-score measure? If you get a Z-score of negative 0.73, what's that about? Yeah, someone also said, that's right. So it's how many standard deviations away from the mean you are. So it's like if you have two distributions with a different mean and standard deviation, it's like you're trying to compare, and you have one observation from one and one observation from the other. It's like trying to compare apples and oranges, right? But if you make them both Z-scores, both those observations Z-scores, then you're comparing apples to apples. How many standard deviations away from their respective mean are they? Okay, so Z-score is a way of standardizing distributions so you can compare things that normally you can't compare because they're different. And that because it's all about number of standard deviations away from the mean. And that's our Z-score, right? So that's what we've been doing recently. Okay, so try this. So then I'll just give you the information here. It says this is the lengths of thumbs of frogs, and they say the mean is 6.71 millimeters, and the standard deviation is 0.67 millimeters. So in general, how can we get the standardized version of x? Z equals So how would we just get this? So this is just a general formula then. Given any frog thumb length, how could we calculate? So given x equals the frog thumb length. This is very important to know the lengths of frog thumbs, right? How would you find, in essence, you'd be finding how many standard deviations above or below the mean that particular observation was. And how would we do that? Miguel, how would I do that?
That would be x minus 6.71 over 0.67.
That's right. Okay, so let's find out. So not only find the z-scores, let's find what percentage of frogs have thumbs between length between 5.2 and 8.1 millimeters. Can you do it? So we'll take this a step farther here. Good practice. Everyone do it. You got your chart? Michael, did you get a z-score for 5.2?
Yeah, -2.25.
You agree with that? Okay. Yvonne, did you get a z-score for 8.1? Okay, so before we even go to the chart, we could make a really pretty close estimation if we remember what this is about. Remember? So 5.2 is like 2 1/4 below, and 8.1 is just about 2 above. So we can make a really close guess before we even go to the chart if we remember how standard deviation works. Anyone want to make a guess? Who does not have a chart with them? You don't have? You forgot. It's great. Okay, so you forgot it. But you can make a pretty good guess. What's your guess?
96%.
96%. How'd you get that? How'd you come up with that?
Well, that's 2 standard deviations on each side.
Is how much?
And so that's 95 normally.
Okay.
So I added 1% to the quarter.
Yeah, so it's excellent. So we know that two standard deviations either side of the mean is about 95% of the data. She's saying, oh, it's a little bit bigger than that, right? It's a little bit slightly bigger range than that, so she's guessing 96%. Okay, what's the area to the left of negative 2.25 according to the chart? What's our area? Anyone got it? 0.0122 is what I'm hearing. So 1220? Oh, 0.00. Oh, right. That's, yeah. I said it and I wrote something different. Okay. 0.0122. Okay. And then what about here? 0.9? 808? Doesn't make sense. Everyone follow that. Okay, and so then this is to the all the area to the left of 2.07. This is all the area to the left of that. So the area between them, you subtract, right? What is it? Just shout it out if you got. What is it?
0.968.
Questions on that? 96.86% of frogs have a thumb length between 5.2 and 8.1 millimeters. Questions? Okay, probability. So let's talk about probability. Remember, the probability of an event is the ratio of, the denominator is the total number of possible outcomes, and then the numerator is of those, of all the possible outcomes, how many of them are the desired event? So the probability of rolling a 5, right? Rolling a 5 is 1/6. Because there's 6 outcomes, one of those 6 is the number 5. And so then what's, of all the possible outcomes, what's the worst you could do? What's the least number of outcomes you could have out of all your possible outcomes? 0, right? So 0 is the worst you can do. Therefore, 0 is the lowest possible probability. And what does it mean? What does 0 probability mean? That zero of those events, of all the possible events, 0 of them qualify. So what's the probability of that occurring? Or when will that occur? Okay, so it's impossible. It never occur. Okay, and then what about, okay, you guys, this isn't cool. I'm giving you guys every Friday off, so you can't just walk out in the middle of class. Sorry. Unless you've got an emergency or somewhere to go. I'm giving you every Friday off. I'm not going to have people, half the class walking out. Sorry. All right? What about if every single event, what's the best we can do with probability? I'm taking attendance, so those people will not be counted here. What's that? All right? So, like, what's the probability that you roll a dice of a number less than 8? So the probability, so you can roll a dice, it's probably going to get less than 8. So how many possible outcomes? 6. And of those 6, how many are less than 8? All of them, right? Can we do any better than that? Can we do any better than all of those being in our desired event? No. So that's the highest probability. You can't do any better than that. 1. So this is highest probability is 1, and it means absolutely certain. It's going to happen every time. So then in between, what was our 0.5 probability then? What does that mean? Happen half the time, or it's equally as likely to happen as not to happen. So then probability is less than 0.5 over here. What do they mean? If 0.5 is equally as likely to happen and as less than happen. Sorry, this is equally likely to happen as not to happen, then what is the probability less than 0.5? Less likely to happen than not, or less likely to happen than to happen. Okay, and then probability is greater than 0.5? More likely to happen. And the closer you get to 1, the more and more likely it is. And the closer you get to 0, the less and less likely an event is to happen. I didn't mean to have that in there. This one. Okay, and so then we saw that probabilities are like the twin of relative frequency. So if we want the probability of, what is this? Table showing female hospitalizations. Okay? The probability that a hospitalization was from an age group of 0 to 19. What would it be? It'd be the relative frequency of that group. It'd be 810 over total number of hospitalizations, whatever that is. So your relative frequency is virtually the same as probability, relative frequency. So the same way that you found the relative frequencies is basically the probability formula. It's the number of the desired event divided by the total number in the group. Okay, and so then we had Venn diagrams. Remember Venn diagrams? Okay, so and then we labeled events with capital letters. Okay, so let A be the event that student likes Mexican food, and B be the event a student likes Korean food. So let's just do a quick, hopefully this will be, I picked good events here. So how many people in here like Mexican food? Not everybody, or almost everybody, all but one? Okay, so how many people are here? 1, 2, 3, 4, 5, 6, 21. So 20 of 21. Okay, how many people like Korean food? Don't be shy. 1, 2, 3. And so how many like both? So was it all 3 like both? So this wasn't a good example. I was trying to think of a good example fast. So I'll just make up some data here. So let's say 16 of 21, I'm going to change it. 16 to 21 like Mexican food. That's our group event A. All right, and then 3 of 21 like Korean food, and then 2 like both. So can we make this Venn diagram and use it to calculate probabilities? Okay, so where am I going to put 16 in the diagram? Nowhere, right? Because the 16 is the total of everyone who likes Mexican food, which includes those who don't like Korean and those who do like Korean food. So what about the 3? Where can I put the 3? Well, same thing. The 3 is the total of everyone who who like Korean food, which is those who also like Mexican and those who don't. Okay, so 2 like both. We can put the 2 there. So that the overlap is the and condition. So 2 like Mexican and Korean. And so therefore, how many like Mexican but not Korean? 14, right? So that the total in the A circle is the 16 for event A. And then what about here? 1. So that the total that like Korean food is 3. And then are we done? So no, because this only accounts for, of the 21 students, 17. Therefore, there's 4 left. And who are those 4 people? Don't like either, right? Don't like either. So this diagram then shows visually what the class is like in terms of these food preferences. Okay? So then we can make a probability Venn diagram out of that. So if we take all those values divided by 21, it makes a diagram that's probability. So 14 out of 21, that's 0.33. Um, 0.66, thank you, 0.67. Other ones, quick. 2 out of 21. 0.095. And this must be 0.19. Oh no, half of that. 0.0425. And then this one be 0.19. Is that right? Okay, and so then what's the probability that a student is in A or B? And remember, this was our probability rule for or. We could do, so we got the 16 out of 21 that like Mexican. We got the 3 out of 21 that like Korean. But then we just double counted, right? We just over counted those who like both. And so we need to subtract off 1 time those who like both, which was 2 like both. So remember that principle that the probability of one event or another happening is, yeah, you sum up those probabilities, but if there's an overlap, you just counted that overlap twice, so you subtracted off once. And that would be the exact same result as what? Just adding together everything in both circles. Here we've actually separated it out. There's no overlap in these numbers, 0.67, 0.095, 0.047. There's no overlap in those. So we can just add those 3 together, and that would be the exact same thing as doing it this way.
Do you have all 3 or just
Am I, so, but this 0.67 is, they like Mexican, but they don't like Korean. And then this is they like both, and this is they like Korean, but they don't like Mexican. So there's no overlap, so you just add them. But this is all students who like Mexican, including Korean. And this is all who like Korean, including Mexican. That's why you have to subtract. Does that make sense? Yeah. Questions on that? Okay, and then from there we went on to chapter 6. So we're going to call it there. Any questions? If you have a question, if you want to ask me a question, I'll stick around. Let me just take attendance real quick, everyone who stayed.